Good afternoon and welcome to Physics 8224, Exploring Black Holes. I'm Professor Ed Bertschinger, and I'll be teaching this along with Dr. Edwin Taylor, and our teaching assistant is Ansi Fakuri, seated in the back. This is an unusual class in a number of respects that we'll be discussing at the beginning here. But the first thing is I'd like to let you know that this 1.5-hour recitation is being videotaped for the benefit of MIT alumni who are watching the class and will be participating in the class from a distance. So welcome, alumni. Let me start with a little bit of the structure of the class. We have a weekly recitation section that will meet at this time, usually not in this room. Our normal meeting place is in Building 1. However, this room gives us the capability for videotaping and having special video displays. That's why we're meeting here for the first classroom meeting. We also have an evening seminar that meets Monday evenings from 7 to 8:30. This seminar doesn't replace or is not a direct substitute for the traditional MIT lecture. Instead, it's a kind of an undergraduate seminar, almost like an undergraduate colloquium, where experts working on black holes and astrophysics come and speak about the research work and discoveries that they're making, allowing you to see how the classroom studies that we have are being translated into and transformed by these exciting discoveries. Let me give a little more of an introduction based on our past website. This is a web-based class, although not entirely, but we make extensive use of the web. We expect you to have access to the websites. And in fact, if you go to the MIT WebSys registration page and look at the online subject listing, online course catalog for the MIT subjects, you'll find a link to the web page for this class. The one I'm displaying now is actually last year's web page. But you see that there is a little pointer here which says that the class has moved. So when you go to the MIT website for the class, you'll get a little dialog box like this. And this is a certificates box. You may have certificates enabled in your web browser. You might not, but you can learn how to do that when you go to the Stellar to the web page. So I'm going to enter my password. Didn't enter it right, I guess. Try that again. And good. And I will click on the student view, and so we'll see the website as you would be seeing it when you enter through this system. Eventually. This website is part of MIT's online classroom technology called Stellar. This is a project of MIT Information Systems. It provides hosting for class web pages, discussion boards, and a lot of other features that you'll be learning about as you take our class. And one of the first things you ought to do then in taking this class is to go to Stellar, find this website, and try logging on. If you've pre-registered for the class as an MIT student, then we have you already entered into the database so that you can access not only the public parts of our web page, but also the discussion boards containing internal discussions, question and answer with you, with the alumni, with the course staff. If you haven't registered for the class and we don't know that you're taking it, then please send me or Dr. Taylor an email so that we can add you to a list of students in the class. The alumni, now let me say a few words about the alumni participation. We first taught this class a year and a half ago in the fall of 2001 as a kind of an educational experiment with support from the Darbeloff Fund for Excellence in Education at MIT. The Darbeloff Fund supports innovative teaching methods. So we were one of the courses that received support, And part of our innovation was to involve alumni taking the course at a distance. This year, we're again including alumni, but the exact role that the alumni play, and indeed that you have in the course, is changed from last year. Not all of those changes are reflected in the online course catalog description. For example, if you go to WebSys and read about this class, you'll find it says that homework is to be submitted electronically. Actually, that's not the case now. You're perfectly welcome to submit handwritten homework, and we will have traditional problem sets in this class. And there are other changes that you'll hear about as we go through this discussion. At this time, I think I'll pass it over to Dr. Taylor to talk more about what's listed at the website and the structure of the course. So let me give you
the... Thank you. I'd like to talk a bit about the textbooks that we're going to use. There's two. One is called Exploring Black Holes, Introduction to General Relativity, that I wrote with one of the grand old men of general relativity named John Wheeler. This is a book which, can you give me this here? Unfortunately, this doesn't reproduce the small type here, but on the back of this book, it explains what the book does and what it doesn't do. The governing equations in general relativity are Einstein's field equations, and they deal with what the book talks about, but also the formation of galaxies, suns, neutron stars, and black holes, also gravitational waves and cosmology. What we do is to talk about stationary structures. It can be a black hole, it can be the sun, it can be the Earth, it can be a spinning black hole, but they are structures that don't change with time. And for such structures, the field equations allow you to derive what are called the metric. And we use two things in this class, the metric and what's called the principle of maximal aging. Those two things are the two big ideas in this class. But because we start with the metric, you don't have to have tensors, you don't have to have differential forms. And unfortunately, we don't talk much about the field equations. The way the book is organized is, again, I apologize for the fuzziness. There are 5 chapters. The first chapter is called Speeding. It's about special relativity. The next one about Curving, which talks about the curvature of space-time. Plunging talks about falling directly into a spherically symmetric structure, such as a black hole. One is Orbiting, which is orbits around such a structure, and one is how light moves in that kind of curved space-time. Then around it are what are called projects, and what's going to happen is many of these will be opportunities for you at the end of the class to do a much more thorough job than is presented in this book. We're going to do 2 projects as part of the class itself. This will be one per week, and an early one includes the global positioning system, which allows you to orient yourself anywhere on Earth within a few meters, and is absolutely useless without general relativity. There's also one, this is called the Friedmann universe, but we're going to have one of the weeks we'll talk about cosmology. There'll be a project that's a replacement for this. So those are that's the part of the book that's the, you might say, the formal part. We're also supplementing this with a book by Kip Thorne called Black Holes and Time Warps, Einstein's Outrageous Legacy. This has got a lot of physics in it. Kip Thorne is also John Wheeler's student, and he's kind of the guru for the LIGO project, the gravitational wave project that's just getting underway. He's a real general relativist. He writes beautifully, and this is in part a story about the people, John Wheeler himself, Einstein, and so forth. So you get the human story in this, as well as a popularized presentation of general relativity. But it supplements, to my mind, perfectly this other treatment, which isn't historical. It just goes through the techniques and the story of general relativity itself. Well, do you want me to talk about some of the later things on this list? Like, because we have a public website, we have to be careful about privacy, and we want you to have a thorough understanding. And on the website is a fuller documentation of what's going to happen. First of all, most parts of the website is available to everybody in the world. They have to log on as guests, and there's various horsings around, but that's available. However, portions of it are available to you, but not to anybody else. The discussion board, for example, will be only available to you and the alumni who are in the class. Your first assignment is to write 1 or 2 pages about the description of a project that you might be interested in. It does not commit you to do that project, but gets you going. And those descriptions which you submit will be available only to people in the class, not outside, because we want you to feel relaxed about not doing a public presentation at that point. The class list is also not available to anybody but you and us. There may be a private archive where we'll put the solutions to the homework. We don't want those on the public website. And the homework submission and grades and the homework solutions may go on a private archive. Then available only to us is homework submissions and the class grades. Now the evening seminars are being digitized and made available, and anyone in the world who wants to log on can view them. And if you don't want to be on the camera, we'll try to keep you off it. The final, this is still part of the privacy policy. The final projects will take about 1/3 of the class, and you'll work in a small group that will include both MIT students and alumni on a project of your choice. We consider this a publication, so that at the end we're going to make the projects, one part of which will be to produce a web page. That'll be public. Anyone can look at it. And your name will be on it. Now, if you don't want your name on the project at the last minute, you can talk to Professor Bertschinger about it. But we consider that a kind of publication. That'll be available for a month after the course is over, and then it will be eliminated. Now, you may know about the OpenCourseWare initiative at MIT. This is not directly a part of that. They're actually providing a little of the funding for this digitization that we're doing. It may be that after the class is over, the class materials will be transferred to the OpenCourseWare site, where anyone in the world can access it and look at it. But there won't be any class lists, no grades, no discussion, no homework submissions, and by then the projects will not be public. Now, there is, as you can see on the sheet here, a woman named Cindy Turbalon, who is a member of the MIT Teaching and Learning Lab. She did a careful evaluation of our last presentation of this class, and this year may sit in on it occasionally. We put her email, and you can send her any comments you have on the class, and she will solicit those comments. She will not tell us who makes comments, but it may be useful to her in seeing how we might want to change it in the future. The grading policy is this: 25% on the homework, which Anzi Fakuri will be grading. There's a midterm exam which actually occurs after the midterm, after we've gotten through the 5 chapters in the book. The final project will be important, and then we want your attention to the last 2 items, but it's not the main point. There will be a series of deadlines about the project so that everything doesn't get put off till the last minute. And we will be giving quizzes in the recitation, mostly concerning the reading, and those plus participation in online discussion will be an increment to the grade. Is there any question about anything I've said so far?
Say a word about collaboration on homework.
Well, I'm now making it up. You're welcome to collaborate on homework. We expect what you submit is your work, and that you take responsibility for it, but there's not a problem if you're talking to each other about things. Am I correct about that? He's nodding his head. How about getting help? I put my name first in the getting help for the following reason. This is my only MIT responsibility. I work at home. There's Cindy Turbalon, who just walked in. I call myself an author. I'm not a general relativist. I'm not a cosmologist. I just write textbooks in general relativity and cosmology with the help of the professionals. I'm available at home almost all the time, almost every day. So you can email me. Ed Bertschinger and I, how many of you use online chat? Not as many as well, half. AOL? A little more than half. We're not used to that. We've just become participants, and this is our little personal contribution to the advanced technology of this class. I'm personally nervous about chat because if you send me a message, I've got to answer right away. And I like to think, and I often have to think. However, we're going to give this a try. If you want to send me an instant message, go ahead. We're not sure about the caps, but that's my moniker. I'm available daytimes. I go to bed early and I get up early. So I know you don't go to, I'm in bed by 9. I know you don't begin your work till 11. So what I recommend is that you'll get stuck on something, send me an email, and then go on. And in the morning, long before you're out of bed, I will have had a chance to answer it. Now, Ed Bertschinger is definitely not retired. He is a general, the good news is he's a general relativist and cosmologist. The bad news is he does a million things. He's teaching another class, he runs a center for cosmology and astrophysics, and so forth. So it's going to be a little harder to get hold of him. In general, I'm supposed to know everything in this book, so that anything here you can ask me about. If it's something that I know a few other things too. But if there's something I really don't know, we'll kick it upstairs to Professor Bertschinger. And I think you will learn as the semester goes by where is the best place to push to get help. I'd like to talk a little bit about the alumni. MIT prides itself on innovation, and there are several innovations in this class. For one thing, although we meet twice a week, there are no lectures, no regular lectures. For another, a lot of the stuff's online. A third is the participation of the alumni. Alumni are very eager. They're very interested in this subject. Last time we offered the course, we asked for volunteers among the alumni. We got 120 applicants for 12 places. Shows you their enthusiasm for it. We chose 12. This time we chose 17 more, so there's approximately the same number of alumni as there are undergraduates. These alumni are very interested in hooking up with the Institute again. They'd like to know what MIT life is like, and only you can tell them that. On the opposite, they know about life after MIT, and there really is life after MIT, and they can tell you about that, right? If you go online and look at the discussions now, we've invited all of you, them included, to make a self-introduction. And I'm always stunned by the range of technical professions that these people are in. Often a single person will have several, what I would call several professions in a row. So these are people that are well acquainted with the technical professional world outside. And we chose people who are very well read in general relativity and cosmology, and they'll bring an entirely new slant to our discussions, which I think will enrich them. It'll be different than I would say, or Ed Bertschinger would say, and perhaps you would say. There's two primary ways that you will interact with the alumni, if you choose. One is on the discussion board, where you ask questions, they ask questions. You can talk about your life, they can talk about theirs. And in the projects. Now, these alumni are used to collaboration professionally. So they do this, so to speak, as part of their profession. And so they'll bring this professional skill of collaboration to the projects when you work on them together. So basically, you're part of an educational innovation whose main feature is a tremendous widening of the community of people that are working together on the subject of the universe, and there isn't any bigger subject than the universe. Okay, do you want to
Okay. Thank you very much, Edwin, for covering the technical aspects of this class. The only thing I would add is that don't put me too far away from the students. I'd love to have email, or if you are on AIM sometime and you have a question about relativity, I hope you'll put me on your buddy list. I've already set up an 8224 group on Messenger for myself, so I'm hoping that some of you will take advantage of our online access that way to ask questions. And this applies equally to the alumni who are watching this and participating in our class. Are there any questions about the formal structure of the class or material that Dr. Taylor presented? Are you ready for a different experience in MIT classes? All right, well, let's see. We're going to switch over now to a discussion of the final projects for the last bit of this recitation. As Dr. Taylor mentioned, roughly 1/3 of the class credit will be based on your collaborative work in putting together a web page and also in giving a presentation to the rest of the class. It's like being a research student giving a presentation in a conference. You'll do a little bit of work for those last few weeks of the class, give the presentation, put together a web page. That's for the last third of the class. But even before that time, you'll be selecting a project, refining it, submitting an outline, joining together in groups to begin formulating your project, having some email or chat exchanges with the alumni at a distance. And so the projects will become an integral part of this class early on. Dr. Taylor and I have given some thought to a set of possible projects for you. Astrophysics and relativity are tremendously exciting fields. There are discoveries being made weekly that are written up in the newspapers. And from these, it's very easy for us and for you to select some topics that could be of interest. So I'll run through a few. And I should add that this material, as well as the handouts or the policies that Dr. Taylor presented, are available at the Stellar website. This presentation isn't yet there, but it will be soon. So you'll have all of this online at your fingertips. Searching for black holes. The title of the textbook is Exploring Black Holes, but astronomers, actually one of the most active areas of research now is searching for black holes, identifying the evidence for black holes. And then we have to ask, how can we see the black holes if they're black? We'll learn about that in this class. The masses of the black holes, other properties, what do they have? How do the black holes form? And a question I don't ask just metaphorically, but rather importantly, how can you search for them while at MIT if you want to? Because there are a lot of MIT researchers doing this work. You could get a UROP working with a group that is searching for and discovering black holes. This topic is really an important one for the whole field of physics, and that importance was recognized with half of the 2002 Physics Nobel Prize awarded to this man, Riccardo Giacconi, who started his life as a researcher working with an MIT physicist, Professor Bruno Rossi, in the late 1950s. Giacconi and Rossi and others invented, essentially, the subject of X-ray astronomy, which is the study of the universe, not through visible light, but through X-rays. X-rays are absorbed by the atmosphere, so they only can be seen from space. And in the citation from the Nobel Committee, which you see here, Following that, there is a little elaboration, some elaboration of the contributions that Professor Giacconi made. And you see at the bottom there the mention that he detected sources of X-rays that most astronomers now consider to contain black holes. So black holes were featured in the Nobel Prize awarded just a few months ago. The spinning black hole. The simplest black hole is the spherically symmetric one. But if the black hole formed from matter that spins, that has angular momentum, the black hole itself will have an aspect to its spatial geometry, its space-time geometry, reflecting that intrinsic spin. And so we'll study briefly in this class, and you may study more as a project, how the spin of the black hole affects the space-time around the black hole. Do particles get sucked into the tornado-like swirl of space-time around a black hole? Can the spin be tapped? The answers to these questions are fascinating, and we think they're not only theoretical questions, but they're related very much to the astronomical discoveries of black holes being made. Here's just an illustrative slide of some of the features of the rotating black hole. On the left, a diagram of the three-dimensional spatial geometry around a spinning black hole. One of the oddities of this so-called Kerr solution, after its discoverer, is that the singularity, the place where the matter and the curvature become infinitely dense, or the curvature becomes infinitely dense, is not a point, but a ring. And what's more, if you fall into a Kerr black hole and have a rocket so that you can navigate your way through and pass through that ring, you might be able to use it to travel to another universe. This diagram on the right-hand side shows something quite different, a space-time diagram of the structure of the black hole, where moving vertically is moving forward in time, moving horizontally is moving in space. And it is possible, theoretically, to travel through the black hole, starting in our universe, and to emerge in another one. That would be a fascinating project for someone to explore, make science fiction become real, at least at the level of the mathematics. So far, I've heard no reports of anyone actually traveling this way. Cosmology, the study of the universe. Just in the last few years, this has become tremendously exciting as we begin to learn about the structure and geometry, the evolution of the universe. We now have evidence that the universe not only is expanding, but its expansion is accelerating and will continue forever. So this, too, is a tremendously rich ground for investigation, some of which we'll do in this class as part of our weekly material, but you might make extensions of it through your own research. In this class, we'll be talking about the diagram on the left, which plots two quantities called omega sub m for matter, omega with the Greek letter lambda for Einstein's cosmological constant. You'll be learning about that in this class. And these two parameters measure the amount of matter in the universe and the strength of this amazing substance called the cosmological constant, or dark energy. A few years ago, astronomers and physicists had really no idea where to put the universe on this diagram. Or I should rather say that each different astronomer had a different idea about where to put the universe on this diagram. But just in the last 4 or 5 years, we're beginning to converge to a solution in this crosshatched area, which suggests that the universe is accelerating and will expand to infinity. And as you'll find in this class, much of the evidence for this comes from study of the microwave radiation permeating the universe left over from the Big Bang. About 10 years ago, a map of the sky was made by a NASA satellite called COBE, Cosmic Background Explorer, like this. This is unfolding the celestial sphere onto the flat plane with the coordinates arranged so that the disk of the Milky Way galaxy goes right through the middle. And the Milky Way shines in microwaves. That's why we see this emission. These are false colors. The actual radiation is in the microwave range, about the frequencies that your microwave oven puts out. Now, For the last 2 years or year and a half or so, NASA has had another orbiting satellite called MAP, the Microwave Anisotropy Probe. They are going to have a press conference next week, I believe, announcing their results, their discovery, and making a map of the sky, there's a pun there, that might look like the one on the bottom. I hope it does, or maybe I should rather say, I hope it doesn't, because either way will be tremendously exciting. Either it will affirm our basic understanding of the universe, or open up the subject for the need of whole new theories and developments. And that's just next week. The global positioning system, Dr. Taylor mentioned that that's part of our curriculum that we'll be covering in the book. But one can go into that in more depth. Global positioning system depends on general relativity for its correct functioning. The global positioning system is a set of satellites orbiting the Earth in this type of a configuration. And on the right panel here is a photograph of one of the advanced generation of GPS satellites under construction. This set of candy canes on the top are a set of antennas that can phase their emission so as to beam the GPS signals to specific locations on the Earth's surface. I suppose putting the signals where people want them and keeping them away from where they don't want them to go. Inside the black hole horizon, the black hole is a unique object. It's got a singularity where the laws of physics break down in the middle, either at a point or in a ring, depending on whether the black hole rotates or not. But that singularity is enshrouded by a surface called the horizon. If you cross the horizon, it's impossible to return to our universe. It may be possible to exit into another one. So you can explore what happens, in principle, if one crosses the horizon. In this class, we'll be studying the properties of the geometry of space, and this will involve coordinates. Coordinates behave in bizarre ways when you cross the horizon of the black hole, and we will study that. Here's a fascinating question. I often get asked this. Could we be inside a black hole right now? Your report on that would be of great interest to us. Here's a little schematic on the left of the space-time geometry of a star collapsing to a black hole. And these things that look like little flashlight cones are the light cones of special relativity showing the direction of light rays emitted, say, from a flashlight, where time is forward, that is vertical, means forward in time, and the conical shape reflects motion in the x direction and the y direction, two directions in space, one in time. One of the problems with general relativity is it's hard to present all the four dimensions, 3 of space and 1 of time, on a single diagram. And so we make compromises like this. What is it like in the center of a black hole? Well, I found a poem by the poet E.E. Cummings that might give a clue. I was considering how within the night's loose sack a star's nibbling infinitesimally devours the darkness, the hungry star which eventually jiggle the bait of dawn and be jerked into eternity, when over my head a shooting star bursts into a stale shriek like an alarm clock. Maybe that is the poet's rendition of the space-time diagram. There are more down-to-Earth or down-to-solar system phenomena that we'll be studying and that you might investigate. The orbits of the planets in the solar system know about general relativity. Well, we learned in high school, I did, and I'm sure you did, that orbits of planets around the sun are ellipses, or they could be parabola or hyperbole, depending on whether the planets or objects are bound. But Einstein proved that's not so with the actual gravity produced in relativity. How did he do that, and what did he find? Well, the title, Perihelion Advance of Mercury, shows that what Einstein found is that the orbits are not closed ellipses, but they're almost closed ellipses whose orientation, whose long axis, slowly changes with time. Grossly exaggerated here for the orbit of Mercury. Mercury is the innermost planet in the solar system, and these effects of relativity fall off with distance from the sun. They're strongest for the planets that move the fastest. Mercury, being the closest to the sun, moves the fastest. This is a very small effect within the solar system, but astronomers study other objects in space where it can be a large effect, because perhaps two neutron stars are closely orbiting, or a neutron star close to a black hole, or a swirling accretion disk of matter orbiting a black hole. And then it becomes really interesting to ask, can we detect this precession effect from the data? Light itself is modified by gravity, the motion of light in particular. Light is slowed down as it passes near the sun. And this has been studied in our solar system, first extensively with the Viking spacecraft in the 1970s and 80s, through the pioneering work of Professor Erwin Shapiro, who at the time he came up with the theory and proposed a test of relativity. He was a research scientist at MIT's Lincoln Laboratory. And his work was brilliant, phenomenal, and he became very quickly a professor of Earth, atmospheric, and planetary sciences and started, in an important way, the development of planetary radar astronomy at MIT. Eventually, he moved to Harvard, where he heads the Harvard-Smithsonian Center for Astrophysics. I found a cute little animation on the web that illustrates this Shapiro time delay. Imagine that the Earth goes around the sun, Mars goes around the sun, and a light signal is sent from Mars to the Earth by one of the spacecraft on Mars. Well, if the path of the light passes close to the sun, then the light takes a little longer. Not very much, much less than 1 second, but that's enough of a lengthening to be very easily measured and used as a fourth test of general relativity. You'll learn about the other 3 tests in our class. Einstein Rings, another effect of the propagation of light. Imagine that you've got a star and a black hole in the foreground. What do you see? Well, you might think you don't see the star because it's obstructed by the horizon of the black hole. But the black hole not only changes the light travel time, it deflects the path of light. The gravity of a black hole, or of any gravitating mass, will bend the path of the light. So if you've got the perfect alignment, star, black hole, and you'll see light deflected around the black hole from all directions, forming what we call an Einstein ring. This effect, called gravitational lensing, has been seen in the universe in a couple of beautiful examples here. At the top is a photograph made with the Hubble Space Telescope. These luminous yellow glowing objects are galaxies containing billions of stars in a cluster called Abell 2218. And you can see also in this picture some bizarrely shaped bluish arcs, blue galaxies. Those are behind the cluster, very far behind the cluster. The cluster is not a black hole, but its mass has a similar effect of bending the paths of light rays, so that we get, in this case, partial arcs. Not perfect ones, because there's not the perfect alignment needed to give this exact circular symmetry. The Einstein ring phenomenon was first discovered from the radio radiation of this bizarre galaxy, which has not only been split into a ring, but part of the emission from that galaxy separated into 2 bright spots. This discovery was made by Jackie Hewitt, who's now a professor of physics at MIT, and she continues in this research. Gravitational radiation. Light travels at the speed of light. The effects of gravity, gravitational radiation, travel at the speed of light. That is how general relativity reconciles gravity with the finite speed that information can propagate. How do we represent gravitational waves? What is a gravitational wave? That's a beautiful subject to study. How are physicists now, at this moment, searching for gravitational waves? There's an instrument called LIGO, Laser Interferometric Gravitational Wave Observatory, that Caltech and MIT are jointly operating, and we'll study it in this class. It uses light to search for gravity, or for gravity waves. And it has this arrangement of mirrors and laser beams that are very sensitive to any changes in the lengths between these pairs of mirrors. Now, if we have two massive objects, like two neutron stars or black holes, orbiting close together somewhere in space, they will cause ripples in the fabric of space-time, something like this spiral pattern at the top. Traveling away from that binary star system at the speed of light, perhaps impinging on the instrument, the LIGO type detectors. And if so, the effect will be to change slightly the lengths of the arms, which can then be recorded in the output of this instrument. This is a simple schematic, but actually building and making one of these interferometers is not a small task, nor are these interferometers small. There are two of them in the US whose arm lengths, where the light travels, are 4,000 meters, 4 kilometers of high vacuum through which lasers travel and measure the geometry of space. In this semester, we'll hear the first announcement of limits on the strength of gravity waves measured by the LIGO instrument, probably in April. I mentioned that if two stars, massive stars, are orbiting close together, they make this spiral pattern in space-time. Well, there are such stars. Neutron stars have been known for more than 30 years now, and a pair of them were studied carefully by Joe Taylor and Russell Hulse, who discovered that the orbit is shrinking in a way that can only be accounted for by the emission of gravitational waves. Now, those gravitational waves haven't directly been discovered, but their effects show up in the energy loss from this binary star. And for that discovery, Taylor and Hulse won the Nobel Prize in Physics in 1993. Here's just a schematic of how they looked at the stars, rotating neutron stars, emitting radio waves like a lighthouse. That's called a pulsar. And then one of those neutron stars emits light, radio waves that we see on Earth. The other one is invisible. We don't know why. Maybe it's also emitting a lighthouse pulse of radiation that just doesn't happen to cross our line of sight. But you can read about this discovery at the Nobel Foundation website. Gammaray bursters. The universe is full of wonderful and amazing things. And one of them that we're just starting to get a handle on in the last year or two are the very brightest sources in the universe, called gamma-ray bursts. For a few seconds, a star, something that appears to be a star anyway, puts out so much radiation that it's brighter or comparable to in brightness all the other stars in the whole universe combined, just for a few seconds. Absolutely astonishing. We think that maybe these events signal the formation of a black hole, and they happen about once a day in the universe, someplace. Look at the bottom left for a moment. This is a map again of the whole sky in gamma rays. The Milky Way galaxy emits some gamma rays from the stars and gas in its plane. And here, out beyond our galaxy, is a spot of light, which in 10 seconds brightens up, and for a brief moment, again, in the gamma rays, becomes brighter than all other celestial gamma ray sources combined. Absolutely astonishing light output. And here you can see the trace of counts per second in the gamma rays made by an orbiting satellite. We're starting to understand, to unravel the nature of these bizarre explosions. And one way is by finding radiation from them in the optical and radio wavelengths. MIT plays a very important role in that work. MIT has a gamma ray satellite called HEDI-2 that discovers these gamma ray bursts and very quickly informs astronomers all around the world that a gamma ray burst has just gone off and giving the direction. Just a couple of months ago, the HEDI satellite got a localization on the sky of this one gamma ray burst very quickly, so that about 1 minute later, 1 minute after the gamma rays flashed, this was seen with optical telescopes. And boy, it was a lucky thing that the identification was made so quickly, because you can see that the optical object on the left next to an ordinary galaxy, and just 9 minutes later, it had faded and was invisible in the optical. But the information we have from those few minutes is helping us to understand how these gamma ray bursts work. Supermassive black holes. Some black holes reside in the centers of galaxies and weigh millions to billions of times as much as our sun. Other black holes appear to form from the collapse of stars and weigh maybe 10 times the mass of the sun. They cause different phenomena. You may have heard of quasars, very luminous sources of optical and X-ray radiation. We think they're powered by supermassive black holes. There's one in the center of our galaxy, a black hole that is, called Sagittarius A star in the constellation of Sagittarius, center of our galaxy. Are we in danger of falling into it? Is the presence of a 2 million solar mass black hole something that we need to worry about in our galaxy? Well, I wonder. The way these are found in quasars and active galaxies is through the tremendous beams of radiation that spit out from, we think, the spin axes of rotating black holes, shooting out relativistic particle beams that make these beautiful whorls of plasma out in interstellar intergalactic space. This picture at the top is not an artist rendition. It's an actual radio image of that radiation emanating from the black hole, impinging on the medium around it. It's actually radiation from the hot plasma, the relativistic plasma produced by the black hole. And on the right, a tantalizing image of the accretion disk, matter, swirling around one of these supermassive black holes, again, at the center of a nearby galaxy. The black holes we discuss, we will focus in this class on classical general relativity, just Einstein's theory of gravity. But one of the great quests for the last century, ever since Einstein's work, has been to try and unify general relativity and quantum mechanics. There's a successful unification of those two without gravity. Quantum field theory combines relativity and all the other laws of physics except for gravity. But gravity has proven very challenging to quantize. Now, one step in that direction was made almost 30 years ago by Stephen Hawking, the famous British physicist, who gave a lecture not long ago as part of the Cambridge MIT Institute here. And he discovered that theoretically that black holes wouldn't live forever, but might evaporate. They could evaporate. And the way this happens is through a process called quantum tunneling that can produce, even in the vacuum of space, a particle-antiparticle pair. The physicist vacuum today is nothing like what we thought the vacuum was, just empty space, hundreds of years ago. There are particles flitting into existence and in and out of existence all the time in the vacuum. And if this happens to take place very close to the horizon of a black hole, a particle may fall in, or an antiparticle, leaving the other to escape. And the effect would be a reduction of mass of the black hole. There are a lot of questions remaining about this process, and some of the most profound questions about quantum gravity could be addressed by superstring theory, a theory maybe of the 22nd century that we're trying to study now in the 21st. Well, we look forward to working with you and the alumni as well in these and other exciting projects. Are there any questions on this presentation of the projects.
You should talk about next seminar and other possible speakers for the seminar.
Okay, just to return to the structure of this class, we have our Monday evening seminar series. Some of these topics that I presented will be gone over in more detail by the evening seminar speakers. On Monday, this coming Monday, we'll meet in this room, 9-151. The seminars will be videotaped. And at that time, I'll be leading a presentation together with Dr. Taylor, where we just have fun going through some of the fun and curious questions that you might have about black holes. So please come. We look forward to your participation in this class. Thank you very much. See you on Monday.